In this video, we're going to talk about related rate problems. So I think it's best just to sort of work through an example, and we'll go kind of step by step, take a look at the example, and then sort of generalize an approach at the end. Okay, so for the first problem we have the radius of a circle is increasing at a rate of 10 feet each per second. How fast is the area of the circle increasing when the radius is 50 feet? Okay, so let's go to Desmos and just take a look at the problem. We have some circle and it is getting bigger, right? The radius is increasing here. So here the radius is getting bigger. And as the radius is getting bigger, right, then so is the area of the circle, right? It is growing also. Okay. So there's a couple of things involved here. The radius, and the area of the circle here. So for instance, right here we have the radius is 30 right here, so that would be the distance is 30. And then the area of the circle is given by pi times the radius squared right here. But as the circle is getting bigger, right, then both those quantities are increasing at some rate per second, right? The radius is increasing at some rate, right? It's getting larger, by some number of feet every second, and the area is also increasing by some number of square feet, right, every second there. So not only do we have the radius and we have the area here, we also have the rates involved, the rates of change over time of the radius and the area. So in related rate problems in general, you're going to have two or more quantities that are changing over time. In this problem, right, we have the area and the radius. So the very first thing that you want to do in these related rate problems is identify those quantities that are changing over time. So here, clearly, it's the area of the circle and the radius of the circle. And we're going to call the area of the circle A and the radius of the circle R. Sometimes in some of these problems, they'll have quantities that are constant, meaning that they do not change, right, over time. And so it's important also to kind of note those quantities as well, because you need to treat those slightly differently than you do the quantities that are changing over time. But here we don't have that situation. Here we have area and radius, right? Those are the two things that are changing. And so therefore, we're going to introduce variables for those, and A and R makes sense in that case. All right, next up, right, those quantities that are changing over time, they're going to be related to each other by some equation, and that's an important part of every one of these related rate problems. So what you need to do is to find the equation involving those quantities that are changing. And so here we already saw that the area of a circle is pi times the radius squared. And in some of these related rate problems, this equation is just going to come from the geometric properties of whatever object that you're looking at. And I'll just give you those. You don't need to memorize all the different formulas or anything like that. Okay, so here the equation is A equals pi times the radius squared. The fundamental assumption that you need to make in all of these related rate problems is that all of the functions involved there are differentiable functions of time variable, right? These quantities, the area and the radius, they are changing over time, right? So the area will be some function of time, right? And the radius will also be some function of time over here. Okay. The thing is that in most of these related rate problems, we'll never know what f of t and g of t are. Let's go back to the example that we had right here. So here I have a equals pi r squared, right? These quantities are changing over time, right? Here I've hidden this the function, but I can see it in this case. Here the radius function is just 10t. That's it. 10 times t. So pretty simple. Okay. So that's how you kind of need to think of all of the quantities that are changing in the equation that you have. Hey, here's A, it's some function of t. And R, it's also some function of t right here. Okay, so in this case, I showed you what it is, but in most of these related rate problems, we'll never really know what's there. All we'll have are these variables here that are changing. Okay. All right, and since we never know what f of t and g of t are most of the time, what that means is that we're going to need to take the derivative, right, implicitly with respect to time. We won't know what the formula is. We won't know what the formula here is, so we'll have to take the derivative implicitly. Why do we need to take the derivative at all? Well, the derivatives, right, give the rate of change of the quantities with respect to time. If you remember right back when we were talking about velocity, velocity was the rate of change of the position with respect to time. And the acceleration was the rate of change of the velocity with respect to time. So these problems are asking about the rates of change of these quantities, and so we will need to take the derivative of these equations with respect to time. Okay, so we're going to take the derivative of the equation implicitly with respect to time. One thing that you need to be a little bit careful of is plugging in the values for R and A or whatever quantities you're dealing with too early. You want to wait until after you take the derivative, and that's extremely important. Okay, if you plug in the quantities before you take the derivative, right, that you're kind of assuming that those quantities are not changing over time, right? If they're fixed, if you plug in a specific number before you take the derivative, and we know that's not the case in this problem. The radius is getting bigger, the area is getting bigger. Okay, so you need to take the derivative and then substitute in any numbers, specific values that you have. Okay, so we're going to take the derivative of this equation implicitly with respect to some variable t, which is time, right? So over here on the right side, I have a, right? And remember, a is taking the place of some more complicated function of t, which I don't know what it is. Actually, we kind of do in this case, but in general, we won't know what this is. And so the derivative of a with respect to t, I don't know what that is. I'm just going to put dA dt there. So that's where I got this. The derivative, whatever function this is, I don't really know what it is, take the derivative of it with respect to t, and that's what I have here. Then I have the equal sign. Over here, I have the number pi times the radius squared. So pi is a constant, right? So what I need to do is take the derivative of a constant times a function. Well, that's the constant multiple rule. The constant multiple rule for derivatives says, hey, just rewrite the constant. So that's what I did right here. And then multiply it times the derivative of r squared. Okay, so that's what I'm about to explain. Okay, so now we just need to multiply by the derivative of r squared. Okay, remember r is taking the place of some more complicated function of t. In this case, we kind of happen to know what it is, right? It's just 10t in this case. But in the other problems, we won't know what that is, and we won't really have to know. Just remember, hey, there's some more complicated formula in here. So what you have to do is take the derivative implicitly. So taking the derivative of r squared, right, becomes a chain rule problem. There's some more complicated formula underneath there. I just don't know what it is. So the chain rule problem says take the derivative of the outside. Here, right, the outside function is just r squared, right? And so the derivative of that by the power rule would be 2 times r. Okay? Then the step 2 of the chain rule, leave the inside part alone, so I don't mess with the r here. Whatever is inside there, you just leave it alone. Okay? And then the third step of the chain rule says multiply by the derivative of the inside part. Well, I don't know what the derivative of the inside part is. Okay? Because I don't know what the formula is. So all I need to do is just put dr dt there. Whatever r happens to be equal to, take its derivative with respect to time there. Okay, so that is the implicit derivative, right, of that equation with respect to the variable t for time. So if you want to think about it in a really simplistic term, is anytime you take the variable, the derivative of a variable in there that's changing, right, you need to multiply by the derivative of that variable with respect to time. Okay, and that's because of the chain rule. Okay, so we've taken the derivative implicitly, and next thing that we need to do is ask, what is the question asking for? It's important to go back to the equation or to the problem statement and figure out what they're asking for. So if we go back and look, right, the key part is where they say how fast is the area of the circle increasing. So they are asking not for the area, the length, or the area itself, or the radius. They're asking for a rate of change. How fast, right? At what rate is the area of the circle increasing? Okay, so when they're talking about a rate that they're asking for, they are talking about the derivative. So they are talking about the rate of change of the area with respect to time, and that is dA dt. So this is the unknown in this equation. That's what they're asking us to find. Okay, so what they'll do is the problem will tell you about every other value, or tell you a value for every one of the other unknowns in the problem. So again, now that you know what you're looking for, you need to go back and figure out what they tell you about the other unknowns in there. Okay, so look through the problem and determine the value of the other quantities and rates. Okay, so they tell us in the problem that the radius of a circle is increasing at a rate of 10 feet each second. So they're talking about the rate of change, right? The circle radius is increasing. It's changing, right, at a rate of 10 feet per second. And they use the word rate. So they are telling us a value for dr dt. So in that little part of the problem, they are telling us that dr dt is equal to 10. Then they say when the radius is 50 feet. So they are giving us a value for the radius, right? They don't say rate of change or anything like that. They say when the radius is 50 feet. So that's just the value of r. This is what I was saying before. One of the common mistakes that people make when they're first doing related rate problems is that they plug in the 50 before they take the derivative. You do not want to do that. Don't plug in any specific values, right, until after you take the derivative, unless, right, you're certain that that quantity is not changing, right? If the quantity is not changing, then you're better off plugging in the constant that it is, right? Like if the radius never changed, right, was always 50 feet, well then it would probably be, you'd probably be better off plugging in 50 feet. But we'll get into that in later problems. Here the radius is definitely changing, right? And so you want to wait until after you take the derivative to plug that in. All right, so we know that dr dt is 10, we know that r is 50, so we can go back to the derivative and plug in those quantities that we know. So we plugged in the 50 for the r, we plugged in the 10 for the dr dt, and just simplify that out, and we'll get an approximation here. So dA dt, the rate of change of the area with respect to time, right, is 3,141.59 square feet per second. So in other words, at that instant, right, when the circle is at has a radius of 50 feet, in the next second or so, right, you're adding about 3,141.59 square feet there. It won't be that exactly in the next second, but that's the rate at that moment there. Okay, and so that's the answer that they're after for this problem. Okay, so some of the general steps for related rate problems. Number one, identify the quantities that are changing. Okay, it's also important to identify any constant quantities. Those are quantities that are involved with the problem that are not changing. Okay. You want to introduce some variables for the changing quantities, right? Like we did for area and radius. For the constant quantities, right, you don't really want to do that. You just want to use the constant number there. Find an equation that relates the quantities. Sometimes that comes from a geometric formula like we had here. Sometimes it will come from the Pythagorean theorem, or there's many other examples. Okay. So once you find that equation, then take the derivative implicitly with respect to time. Assume that all variables in there are differentiable functions of time and take the derivative implicitly. Okay, once you do that, you want to look through the problem for what you're trying to find, the unknown, right? And then all of the other values in there, you should be able to find all the other quantities in the derivative. You should be able to find known values for those by looking at the statement of the problem. So you would substitute those in and then solve for the unknown.